Okay, so page 13.
Yeah. Yeah. Because I don't know. But I'm feeling very yeah. It's like I do. It's like
Okay, so page 13. We talked about natural log functions yesterday, or yesterday and the day before. Today we're going to talk about exponential functions, e to the x. Yesterday we talked about inverse functions and how there's a certain relationship in terms of the inverse. There's e to the x and natural log are also inverses of each other. So they have a way of, but for us, what we're going to see mainly is that they have a way of canceling each other out. We're going to use their canceling abilities for our benefit. So example 1 and 2, we're just going to practice solving exponential and log functions from an algebraic perspective, and then we'll move into the derivative for exponential function base e. So number 1, we have 7 is equal to e to the x plus 1. Anytime we want to solve, or anytime we want to work with an exponent variable, it's hard to algebraically to work with it because there's less algebra properties available for exponents. So anytime our variable is stuck in the exponent, we always try to find a way to bring it down. And the easy way to bring it down is if it's part of a natural log expression. So here I would take the natural log of both sides, because this opens up our possibility of bringing that exponent down. And if the exponent variable can come down, there's a lot more algebraic rules for us to help us move forward. So the x plus 1 comes down, and now we're just trying to solve for x. What do you know about natural log of e? What's natural log of e equal to? Yeah, just equal to 1, right? So that's nice. That goes away. And really, it's just natural log of 7 is equal to x plus 1 to solve for x. Subtract 1 from both sides. Okay, number 2. Solve natural log of 2x minus 3 is equal to 5. Just like how we use natural log to help with our exponential function base e, we're going to involve exponential base function base e to help us with this natural log problem. The issue here is I want to solve for x, but x is stuck inside the natural log. So we want to release that x away from that natural log. And because e and natural log have a way of canceling each other out, we're going to do this. We're going to raise both sides with e as the base. Just like how natural log of e cancels out, e to the natural log also cancels out. So this will allow us to cancel each other out. I'm just left with this 2x minus 3. The reason why these cancel out is because this is log base e. So if I have e raised to the log of the same base, they essentially have that undoing canceling out property. And so because they cancel out, we're just left with 2x minus 3, so it'll be e to the fifth. Before, the x was stuck inside the natural log. Now it's being released. Now it's easy for us to solve for x. It's no longer inside a log expression. But we've also balanced out what we did on the left side with on the right side. So that 5 is now turned into e to the fifth, but that allows us to solve for x. So now I can add 3 to both sides. Then to solve for x, just divide everything by 2. All right, any questions? All right, a couple more reminders regarding properties. If I have the same base, e to the a times e to the b, I can turn that into e to the a plus b. If I have the division of two different bases, I can write that base once and then just subtract the bases. Okay. Remember, e is a number. E is around 2.7, so e squared's derivative is just going to be 0. It does not turn into 2e. We can't treat this like power rule and bring that 2 down, because e squared is just like 2.7 squared. It's just some number. Any constant's derivative is just going to be 0. All right, so here's the rule that is involving exponential function base e. So I would say the 3 big rules that you're guaranteed to see on the AP exam derivative-wise is power rule, natural log, which u prime over u, and then exponential function base e to the u times u prime. We're also going to learn trig rules next unit. There's also logs of other bases. There's also exponential functions of other bases. But these are the big 3: power rule, natural log, and exponential function base e. These are guaranteed to show up on the AP exam. And these are the 3 that we're going to see more often than the others. Okay, so here's our rule here. Derivative of e to the u. The nice thing about e to the u is that the derivative is just itself, mostly. So any function e to the u is just itself times whatever the exponent's derivative is. So before we do example 3, which is a little bit more involved, let me do a couple more here. Let me do a couple of quick examples. So let's say I have y equals e to the x. Y prime, if I want to apply the rule for e to the u, it's just what? The function itself, so e to the x times, what's the exponent's derivative? X's derivative is just what? What's x's derivative? Just what? 1. Yeah. So e to the x times 1. So y prime is just e to the x. Now, something that is more involved here, let's say I have y is equal to e to the 2x minus x cubed. So the derivative of e to the u is just the function itself times the exponent's derivative. So what do we write down first? What's the function itself? Yeah. So we copy everything down like as if nothing has changed, because the function is the derivative. But that exponent, we got to worry about it. So times, what's u prime going to be? 2 minus 3x squared. Yeah. So really, we just have to worry about the exponent's derivative. But the nice thing about e to the u is it's basically just itself, right? If you just copy down the exact same problem, you basically have most of the derivative. Okay, example 3 gets a little bit more involved. So a couple of rules that we want to kind of keep in mind. First, we have natural log of u, which is u prime over u. And then we also want to keep in mind the rule for e to the u, which is e to the u times u prime. So the larger rule at play is natural log, right? That we got to deal with the e to the x, but that comes a little bit later. So right now, we just want to understand that the larger rule is natural log of u. We want to treat this whole thing as our u value. So our big rule that we're starting with is u prime over u. Once we're inside u prime, we may have to do a little bit more because there's multiple terms that we have to worry about. But we can start off with this rule here. Okay, so u prime is asking for this entire parentheses derivative. There's two terms here, so we just have to take one term at a time. So u prime is going to go in this numerator space, just like how the natural log of rule is telling us to do. Okay, so u prime, we'll just take one term at a time. 2x becomes what? 2 minus, okay, so now we're on to the e to the u rule. So e to the negative 2x becomes what? The original function itself. So e to the negative 2x times what? Negative 2. Yeah. So e to the negative 2x times negative 2. All right. So power rule for the 2x, and then exponential base e for that. But as we do that, all we've done so far is we've done the u prime within this larger natural log rule. Okay, divided by what goes down here. Yeah, the original parentheses, right? Okay, so as far as cleanup goes, and if we want to resolve the negative exponent, we can push this to the denominator within the space, though. We can't push this down to this denominator. It's connected to that plus sign there. So the best we can do if we want to resolve the negative exponent you may feel like, oh, I can push this whole thing down to this denominator, but that plus sign prevents us from doing it. The best we can do is create an own fraction within this space. Okay, we're going to combine more and more rules here. Number 4. So we have e to the u, definitely. There's also an x in front. We want to find the derivative. What rule do you see besides e to the u and power rule? Do you see anything larger that we have to make sure we include as part of the process? Okay. How many functions do you see? Or what operation do you see between x and e? What's happening here? They're being multiplied. So guess what we have to use? Product rule. Yeah. So x is one thing. E to the exponent is another thing. These are connected by multiplication. We got to go with the product rule. And G prime is going to be a little longer here. Okay, F prime, X becomes 1. G function, no changes. Back to F, F no changes. Now this is e to the u times u prime. So we got to go through some nested chain rule here. So we know that for exponential function base e, basically the function is going to show up in the derivative, right? The rule for e to the u is just e to the u times u prime. So I know I'm going to copy down the entire function. That's part of my derivative. And then u prime is asking for the derivative of all this here. And then guess what we have to do if we want to find the derivative of this portion? It's a chain rule. Yep, there's an outside inside here. So within u prime, we got to deal with outside inside. So it's a lot going on, a lot of nested relationship here within our derivative. So for this space, we're going to take the derivative of this expression. So outside derivative first, 3 parentheses squared, keep the inside intact, times the inside derivative, which is what? 2x plus 2. Okay. So it's a big mess, right? So again, this part is the part that's most complicated. The rule for e to the u is e to the u times u prime. And because u prime requires chain rule, because there's a lot going on here, it's like its own separate problem. We got to go through chain rule just for that u prime portion of my exponential function rule. Okay, number 5. Write the equation of a tangent line. So we want to gather ordered pair, we want to gather slope, and then point slope form. Okay, so we have our ordered pair that's given to us. We just have to figure out the derivative, and from the derivative, we can find the slope. To find the derivative, what do we have to involve besides e to the x and natural log? Product rule, yeah. E to the negative x is being multiplied with natural log of x. These are 2 distinct expressions. We got to go through product rule to find the derivative. Okay, so e to the u is e to the u times u prime, right? So e to the negative x becomes what? The original function, unchanged, times, what's the exponent's derivative? Times -1. So that takes care of g prime. F function, no changes. G function, no changes. Back to f, no changes. And then g prime, what's the derivative for natural log of x? Just 1 over x, yeah. Let me do a little bit of cleanup here. This is the same thing as negative natural log of x over e to the x plus 1 over x e to the x. Right. Within each a term, I'm just trying to get fractions with the negative exponents resolved. And now from my derivative, I can find my slope. Plug in the 1 to find my slope. Okay. What do you know about natural log of 1? Natural log of 1 is just what? Okay. We know natural log of e is 1, but natural log of 1 is 0. Yeah, so that's nice. That wipes this out. So my slope is just 1 over e. So my point is 1, 0. My slope is 1 over e. Point slope form. Okay, so we've seen product rule, we've seen chain rule, we've seen combination of different rules, and now there's one more thing, is implicit. So implicit is where y's gets mixed into the equation, and we got to keep track of our dy dx's, as well as other derivative rules. So let's look at example 6. Okay, we want to find the derivative x e to the y minus 10x plus 3y equals 0. We know there's implicit even without the problem telling us, because we see y's a little bit out of place. We need power rule, we need exponential function, and there's one more thing we don't want to miss. What else is involved as part of our derivative process? I want to make sure that we can see it because it's a big part of our problem here. Yeah, that x e to the y, it kind of flies on the radar. I know we don't see a set of parentheses. Sometimes if the parentheses were there, maybe it'll help us, but we have to be able to recognize, oh, these are two separate functions. They're being multiplied. This is not one term here. These are two separate terms. We got to go through product rule there. Okay, so we'll set up using product rule. So this whole thing is just for that x e to the y. Okay, f prime, x becomes 1. G function, no changes. F, no changes. Okay. G prime is e to the y's derivative. What's e to the y's derivative? The function itself, right? Times, what's the exponent's derivative? What's y's derivative? 1 times dy dx, right? We're asking for y's derivative. We got to keep track of that dy dx. Right? And we knew that at the very beginning of the problem, we see two different instances of y's. We should be expecting two dy dx's to show up as part of our derivative process. Right? Minus 10x becomes 10. 3y becomes 3 dy dx. Yeah. Okay, so we're done with the calculus. Now we're just trying to figure out how can I arrange these in a way where I can group the dy dx terms together so I can factor it out, and I just have to get that by itself. Okay, so now it's just clean up. So I see two terms that have dy dx connected to them, so I want to leave these on the left side. That way, I can eventually factor that out and get that by itself. But I'll leave these on the left side, and everything else I'll move to the other side. Divide the parentheses over, and then once I get dy dx by itself, I have my answer. I have my slope formula, I have my derivative. Again, a derivative is just doing the job of describing the slope behavior of my original graph, whatever my original graph looks like. So whatever this curve looks like, this can help locate the steepness of any point on the original curve. Okay, number 7. 7, we have implicit as well, similar to example 6, but it's just taking it one step further and asking for the tangent line equation. So we'll find, they're giving us the order pair. We'll find the derivative, plug in the order pair, find the slope, and then point slope form. Right, so we have order pair, so we can get that, we can come back to that when we need it. But first things first, we need to find the derivative. What process do we have to make sure we involve as we think about the derivative? Product rule, how many times? Twice, yeah, xt to the y, that's one instance where product rule will be applied. Y to the x, that's another instance where product rule is applied. And then because you see y's all over the place, there's also what? Implicit, right? How many dy dx's do you expect to show up? 2, yeah, there's 2 separate y variables. We should be expecting 2 different dy dx's. Okay, all right, so product rule twice. So that first set of terms is for my first product rule, and then we got to do a second set here. By the way, you don't have to do all this f prime g plus fg prime as part of your work. I'm just doing it just for demonstration purposes, but you don't have to have that. But if it helps, that's fine. So f prime, 1. G function, no changes. Back to f, no changes. And g prime, e to the y's derivative is what? The original function, right? E to the y times dy dx. All right, so now my second set of product rule. F prime, what's y's derivative? Just dy dx, right? 1 dy dx. G function, no changes. F, no changes. G prime, what's the derivative for e to the x? Just what? Just e to the x, right? Anytime you see an exponential function, just keep in mind that the original function will show up in the derivative, right? So you're just literally copying down what you see. Okay. E to the x times 1, right? And then equals what? Does that stay a 1? Turns into a what? 0. Now, this problem is not asking for the derivative equation. So the bit of a shortcut that we can do is we don't have to hold on to all our x's and y's because they're all going to turn into zeros and ones. So to speed up the process, because it's only asking us for tangent equation, we can just go ahead and start inserting 0 and 1. That will clean up a lot of things. And then once we isolate dy dx, then that's going to be our slope. So the slight shortcut here is rather than spending all that time trying to get dy dx by itself, let's just go ahead and replace all the zeros and ones, and then with in for our x's and y's, and then whatever's left over will be our slope value. Right, so I'll replace every x with 0. I'll replace every y with 1. And we should see a lot of things go away here. So anything times 0 is just 0, so that wipes out. Anything to the first power is just itself. What's anything raised to the 0 power? 1, good. So this becomes a 0, it becomes a 1. So I have e plus 1 dy dx plus 1 is equal to 0. So if I can solve for dy dx, my resulting value is my slope. So dy dx is just -1 minus e. That's our slope. So we have our order pair. We have our slope. And then point slope form. Okay, example 8, find the second derivative. Let's try that. All right, let's do one thing at a time here. Let's first find f prime first. To find f prime, what rule can we apply here? What do you see? 3 plus 2x times e to the negative 3x. Besides the obvious power rule and exponential function base e, there's also what? Product rule. Okay, try that. So try product rule. And then we'll compare our answers and we'll move on to second derivative. Try that first. Okay, what does e to the negative 3x become? First, copy down the problem, right? Because the derivative is just the function itself times what? Times negative 3. All right, here's my cleanup for f prime. I can push this down to the denominator. I can merge it into a fraction, and then to find a second derivative, maybe I can go through a quotient rule here. All right, so here's our halfway point. Okay. To find the second derivative, I'll go through quotient rule. There's my f, there's my g, f prime g minus fg prime all over g squared. Okay. F prime times g, back to f times g prime. E to the u becomes e to the u times u prime. All over denominator squared. Don't forget about that portion. So it's e to the 3x squared. Now, the squared is at the same level as this exponent, so we're really just going to be multiplying these together. Let me do some cleanup here. I can actually factor an e to the 3x out from all three terms, and I can cancel out one of the e to the 3x below. Okay, your homework. Page 16, 17, and 18. odds. So the link that I sent you yesterday has the key on it, but I can send a reminder this afternoon as well as the link to the key. And you'll just be doing the odd number problems. And you're just practicing e to the u, natural log of u, and combination of product rule, chain rule, and finding tangent line equation. All right, come get your phones.
Thank you.
Page 22, great, thank you.
Yeah, 17. Yeah. Not French.